So today we're going to go over some of the equations that we've developed so far based on our definitions, and I'm going to show you two new ones that you need to be aware of, and I'm going to go through some examples of those. So just to review here in terms of our symbols, because this is really important, we have something like this where we write x with a sub I, and we know that this is the beginning or initial position. Beginning or initial position, okay? So we talk about that. I stands for initial if you prefer. That's what I'll use. But that just means where you're starting out anytime you see an I. Then we would have XF, and that stands for our final position. Nothing new here. But I can't stress enough how important these symbols are. Then we had delta X, and that stands for change in position. Another way of saying that, delta X, is the displacement, because a displacement is a change of position. And we came up with an equation for that where we said delta X, whoops, I need a different color here because all the operators I'm going to do in black today, equals our final position minus our initial position. So that's not new. We did that in the last unit. But I have to look at this again to make sure that we are clear on what these symbols are. The symbols are really important here. So this is one relationship that we have, okay? And then in our last unit, we also talked about this symbol, V with a bar over it. And we know that means average velocity. Now, we also had average speed, but once we start talking about acceleration, we're all talking about vectors, so I'm just going to be dealing with this one here. So that's a symbol that we have, and in that symbol there, we've also got these guys, because now we have to concern ourselves with VF. What do you suppose that's going to be? That'll be our final velocity. So if we're looking at a problem, we're looking at the beginning and the end. We might want to know how fast it's going, or we might be given how fast it's going. We could also be given an initial velocity. And initial velocity here is symbolized with VI. So far, velocity, there we go. So far, so good. Shouldn't be too confusing at this point. Using this same idea here, this triangle, which actually I guess I should have made black, because it is a change in position, we could do the same for velocity. We could say a change in velocity. Well, what is that going to equal? Well, that's going to equal the same thing it did over here, only we're using V's. Final velocity minus our initial velocity. Okay? So there is another equation, if you will, that we could have. All right. So not a lot of new things here. Also from the third unit, one other thing I should add here, the symbol for time, T stands for time. And we had one other equation that we developed in our last unit, which was average velocity. This is all old school here, equals, well, it's the displacement, delta X, divided by a certain amount of time. So we've got this relationship here as well. So all of this stuff, this one here, we didn't really talk about too much in the last unit, but it makes sense coming out of this one, what that means. I can't stress enough for you that identifying these symbols becomes really important to doing these problems. Those that have been skipping the problem solving steps, you're going to have a real tough time in this section because you have not been doing this, and you're going to say, oh, I can't do the problem because I can't see it. That's something to keep in mind. So in the last video you saw, let me just cordon this off here a little bit. In the video that you watched the last time, we started talking about average acceleration. So A with a line on top is average acceleration. And I'm going to do my best in this video here to color code things so they're always the same. If I'm talking about a velocity, it'll always be in green. If I'm talking about a position or a displacement, it'll be in purple. If I'm talking about acceleration, it'll be in red. If I'm talking about time, that's in brown. I don't know if you can tell that that's different. Maybe you can, maybe you can't. So from the video that you watched on Monday or Tuesday this week, we came up with our definition for average acceleration. It's a change in velocity over time. So if we're writing that down, and this should not be new, acceleration would equal here a change in velocity, delta V, divided by a certain amount of time. Okay? So here, I guess I should have put this up here. I'll do this below here. Delta V, what does this mean? That means a change in the velocity. Should have probably added it up there, but we've got it there. So you're familiar with this one, although this expression here can be done in a slightly different fashion, which oftentimes becomes more useful to us. I could write it this way. Acceleration equals, now watch what I'm going to do here. Acceleration here equals, well, a change in velocity. What is a change in velocity? Final velocity minus initial velocity. So I could write this one this way. My final velocity minus my initial velocity, all divided by the amount of time that change took to take place, would give me an acceleration. So these are the mathematical ways of looking at these, okay? There are two other equations that I need to show you here. Now, I'm not going to go through how these equations come up right now. I'm going to make a second video. It will be attached to this. So if you're interested to see where these two equations come from, you can look at that video and I'll show you. It's pretty mathy, not necessary for you to know how to do that. But for those that are interested, I'll do that for you. And those two final equations look like this. The first one is the displacement, delta x, equals, these look massive, but if you think about it in terms of the colors that I'm doing here and what the symbols stand for, they become quite useful. So the displacement, delta x, equals the initial velocity times the time, so that's VI times t, plus 1/2. This 1/2 gets stuck in there, times the acceleration, that's the average acceleration, times time, but we have to square whatever that time is. And I'll do an example problem later where we'll look at this expression. So believe it or not, this expression here comes out of an understanding of these guys that we've written down up here. Okay, so that's one of our what are called kinematic equations. This is also a kinematic equation. These two, I should have put boxes around these, are two acceleration equations here, are kinematic equations, and this is a kinematic equation, okay? So that's one, very useful. Why is this one useful? What do I not need to know here to solve this problem? To figure out the displacement, all I need to know is how fast I started out at, how long I'm accelerating, and what the acceleration is. I don't need a final velocity to figure out a displacement here. So that's a powerful expression that we can use. The next expression I want to talk about looks like this. Our final velocity squared equals our initial velocity squared plus the number 2 times the acceleration times our displacement. And what is powerful about this expression is all I need to know here is what I start at, what I end up at in terms of my velocity, the acceleration, and I can figure out the displacement. I do not need to know what the time is for it to take place. So looking through here, again, this looks like a lot, and I know it is. You know, if you need to pause the video to get your notes down, please do so. But looking at this, this was from last unit, that's not new. That was from last unit, that's not new. In the video Monday, we got these things here, okay? And these are the two new ones that were listed here. I don't know if you can hear my cat, but she's a little mad that I'm not paying attention to her. But I will soldier on here. So with this idea in mind, I'm going to use these expressions and go through some example problems so you can see what these look like. So the first example problem that I want to look at is this example problem here. So in this particular case, I have a car that starts from rest, accelerates to the right at 1.5 meters per second. Remember, an acceleration is a vector property, okay? So we've got a car accelerates to the right, starts from rest at 1.5 meters per second squared. There's that acceleration unit for 10 seconds. What is the car's displacement? So when we look at a page like this, let me get that page back out here for us. This seems pretty overwhelming. We need to extract from this page here the right equation and the information to solve a problem like this. And I know this is why students run into issues when they're doing these types of problems. Well, if we follow our problem solving steps, we shouldn't have any issues. Let's try it. First thing, we'll draw a picture. Car is going in this direction. Okay, starts here, and then I'll just draw it this way, goes faster, and then by the end of the 10 seconds, it's really flying along because it's accelerating. So there is my picture. So that's good. What's the next thing we do? We write down our givens. This is the most important part of doing these problems right here, okay? So I read this along, and we come down here and we see accelerates to the right at 1.5 meters per second squared. So 1.5 meters per second squared, that has to be my acceleration. Two ways that I know. It says acceleration, number one. Number two, the units here are acceleration units. So we know that. We keep looking through and we see 10 seconds. Well, 10 seconds, we can write it down. 10 seconds, well, that's a time. So that's looking pretty good. We go further, what's the car's displacement? So now I can write down displacement with a question mark. Okay, whoops, I should have circled this in purple here because that's what we're looking for because I'm color coding all of these. So now that we look at that, there is one given that we are not getting here. And that one given is right here. Starts from rest. What is your velocity if you are starting from rest? What is the initial velocity if I'm starting from rest? Well, that would be 0 meters per second. To a physics type, if I'm starting from rest, my initial velocity is 0 meters per second. If I'm coming to rest, in other words, I'm going along, but I'm slowing down and coming to a stop, if I'm coming to a stop, then my final velocity would be 0. So now we have our givens that we were given in the problem, and we have our what we're looking for. This is the most important part of doing these problems here. Recognizing what the number is, recognizing the unit, and knowing what symbol they stand for. If you can't do that, the rest of this becomes really difficult to do. So with that in mind, we'll pull our equations back here. And now as we're looking at the equations here, we can start to see these are the same equations I had on this sheet, but I'm just going to use this one. It's a little bit smaller. We can see it a little bit better. So here I'm looking for the displacement. So I might think, oh, this equation's for displacement, but in order to use this equation, I need the final and the initial positions, and I don't have those, okay? So we go on. Here is displacement here, but in order to use this one, I need time. That's good. I have time there, but I don't have average velocity here. So I can't use that one. We can keep going along. It shows up in this expression. Displacement is here. In order to do that, I need the initial velocity, which I have, time, which I have, acceleration, which I have, time, which I have. So that's the equation that I'm going to use for this problem. So let's write that equation down. And that equation, because this is step 3, we would say our displacement equals, and then we have our initial velocity times our time plus 1/2 the acceleration times our time, but whatever that time is, we have to square it. So notice all I've done here is written this expression here, right here, okay? Where did that expression come from? That was one of those new ones that I gave you. It's this expression right here. And I've written it down there. So I don't have to rearrange this one here because I'm looking for displacement. That looks great. So now before I plug in the numbers, I have to check my units. Always check your units. And I'll do the unit check here in the same color that we have above. The unit on initial velocity is meters per second times the unit on time is seconds. And then we would say plus, well, I don't need to worry about 1/2, it doesn't have units. The acceleration is meters per second squared times, well, it's time squared, so that would be seconds squared. So here I have seconds squared over seconds squared, they cancel. Here I have seconds on top, seconds on the bottom, they cancel. So if I add a meter to a meter, what do I get? I get a meter, which is what a displacement should be. So I'm good there. So now all I have to do is put in my values and I can solve this question. So my values that I would put in here, well, 0 times 10 seconds is 0. So I'm just going to write, I'm not even going to put anything in there because I know that that's 0. Oh, we'll put it in. We'll put in 0 meters per second times our time here of 10 seconds. But we know that that's going to add up to 0 or multiply to 0 plus 1/2 our acceleration. Our acceleration was 1.5 meters per second squared times, well, we'll do it this way, times our time, which was 10 seconds, but I have to square the seconds, okay? Now you get out your calculator, punch all the numbers in, and if you're punching in the numbers in correctly, you would end up with 75 meters. Now we need to know the direction. I'm accelerating in this direction, so it's going to be to the right because my acceleration was to the right. So that's one problem. We're going to look at one other one here. I'll leave this up here for a second. If you want to stop, you can look at it or you can pause the video. So there's one other one that I would like to look at, and it is this one here. Here we've got an airplane. The airplane lands at 87 meters per second to the right and comes to a stop. The acceleration of the plane is -2 meters per second squared. What is the displacement of the airplane? So in this particular case, this is why drawing pictures in this are really important. I think 3 little pictures here. So here's my airplane. Try to draw an airplane here. Yeah, there it sort of looks like an airplane or a bird. There's my airplane. It's just landed and it's moving pretty quick. And then down here, the airplane again, draw it up here if we can. It's going a little slower. And then finally, the airplane has come to a stop. So here it stops. So there's my picture. So now let's go ahead and write down the things that we have. The airplane lands at 87 meters per second to the right. 87 meters per second to the right. Well, what is that? Well, here, let's go on. And comes to a stop. If I come to a stop, I am 0 meters per second. So these are both velocities. One of them has to be the initial velocity in the problem. The other has to be the final velocity in the problem. Well, when it lands, it's doing 87. And then at the very end, it's going at 0. So this must be the final velocity. This must be the initial velocity. I can't stress this enough. Too many students want to be able to look at this question and be able to see how to do the problem in their head right off the bat, and that's why they get really stuck. You have to work through each one. So here we've got our stop. That was our final velocity. We started out at 87 meters per second. That's our initial velocity to the right. We go on, and here it says the acceleration of the plane is -2 meters per second. So we'll write meters per second squared. So we'll write that down, -2 meters per second squared. And that has to be our average acceleration here. And we read on, what is the displacement of the plane? So again, we're looking for displacement. We don't know what that is. So that's where we start this problem off. This is where students run into an issue. When you're working on these problems, At a minimum, you've got to draw a picture so you have an idea, is the thing speeding up or slowing down? Well, as the airplane lands, it is accelerating in the negative direction. That's why it's negative. It's slowing down. Okay, and then being able to identify what you have, because once you have that in your brain and you've written this down, and yes, this takes mental energy. This is why students struggle here, because they're like, oh, I don't know what these things are. I can't do it. I'll wait until Ms. Nielsen or Mr. Willauer does the problem. This is where you have to do the work right here, steps 2 and 3. Okay, so now what equation are we going to use? I'm going to use this page again because it's a little bit cleaner. Again, we're looking for displacement. So we can't use that because we don't know the initial and final. These are the only things we know in this problem. We go all the way through. We can't use the one I just did because what do I not have here? I don't have the time. I did not identify a time here, so I can't use that equation. This equation here, let's see what we have. Do we have a final velocity? We do, it's 0. And again, it's 0 here because it came to a stop. Do we have an initial velocity? We do. When it landed, it was going 87 meters per second. We're given an acceleration, and the only thing we don't know is the displacement. So when you're doing this, you want to find an equation where you know everything in it except for what you're looking for. So this is the equation I'm going to use in this case. So I'll write that one down here for us. So that's final velocity squared equals, I'm going to put a square there because I know I need it, the initial velocity squared plus 2 times the acceleration times the displacement. So that's the expression I want. In this case, though, I do need to do some rearranging here, okay? Because I don't have this one all by itself. So the first thing I'm going to notice here is that this side of the equation is going to be 0 because the final velocity is 0. 0 squared is 0. So I'm just going to say 0 here, and this will make doing this a little bit easier, equals my initial velocity squared plus 2a times delta x. So I'm going to just subtract vi squared from both sides. So I'm going to get minus vi, whoops, the minus should be a negative now because I subtracted it, squared, equals 2 times the acceleration times delta x. And now all I have to do is divide both sides by 2a, and that'll give me delta x all by itself. So I'll do that real quick. Divided by 2a on this side. And whatever I do on one side, I have to do to the other, 2a. And now the 2's cancel, the a's cancel. So I'm left with my equation here, which is delta x, because that's the only thing that I have left over here. I'm just going to write it on this side, equals minus my initial velocity squared divided by 2 times the acceleration. So now that took some work to get from our initial equation to the equation we want. Once that's in place here, we can check our units. So we'll go ahead and do that. The units on initial velocity were meters per second, but I'm squaring them. So that's meters squared over second squared, all over 2. Well, we don't need the 2. There are no units on that, times the acceleration, which was meters over second squared. Well, I've got a second squared here, here. Those cancel. I have 1 meter on the bottom, and I have meters squared on top, so that one cancels there. And I'm left with meters, so I know I set it up right. So now I can go ahead and solve for the final answer. So the displacement here is going to equal minus, what was the initial velocity? It was 87 meters per second, but keep in mind that that's all squared, divided by 2 times negative, whoops, I got the wrong thing here, times negative 2.0 meters per second squared. And if we have that, then we can get our answer here. I don't think I got my answer out here. Let me find out what we have here. 87 squared divided by 2 divided by that. Whoops, I got the wrong one here. 87 squared, my fault. Divided by 2 divided by -2. I end up with 1,892 meters, and that would be to the right. So when this airplane landed, it traveled 1,892 meters until it came to a full stop. So that ends this part here. I am going to make another video showing where these two equations come from. You're not required to watch them, but I think there might be some that are interested. So that's all I have for today.